All right, let's jump right in. Welcome to this explainer, where we're going to unpack a really fascinating and honestly, potentially destructive issue that might be quietly unfolding on your factory floor right at this very moment. Today, we're diving into the hidden mechanical dangers of mixing your standard industrial motors with modern variable frequency drives, or VFDs. It's one of those combinations that looks absolutely perfect on paper, but actually hides a major thermal threat. To really wrap our heads around the massive scale of this issue, you just need to know one foundational number, and that's 85%. A staggering 85% of industries rely on the standard three-phase induction motor as their primary everyday workhorse. I mean, they're literally everywhere. But as facilities modernize and upgrade how they control these vital machines, a dangerous compatibility gap is opening up, one that's costing companies some serious time and money.
So here is our roadmap for today's explainer. 1. Standard motors versus VFDs. 2. The overheating problem. 3. Inverter duty motors explained. 4. The minimum speed rule. And finally, 5. Practical industrial realities.
Okay, kicking things off with Section 1, Standard Motors versus VFDs. When it comes to firing up an induction motor, you've got a few main options. Traditional setups like a direct online or DOL starter give you a massive amount of starting torque, but that high torque creates a really harsh, violent starting jerk that puts a ton of stress on the machinery. You could go with a star-delta starter, sure, but lately the big trend is moving toward variable frequency drives, and adding a VFD is brilliant, honestly, because it completely eliminates that starting jerk. It gives the motor this perfectly buttery smooth start while also letting you control its speed. Sounds like the ultimate upgrade, right?
Well, that brings us right into Section 2, the overheating problem.
See, while smooth starts are fantastic, slapping a VFD onto a standard motor creates a really dangerous bottleneck if you drop the speed too much. It's basically a mechanical cascade of failure. Think about how a standard induction motor is built. Right there on the end cover, there's a cooling fan, and that fan is attached directly to the motor's shaft. Its one and only job is to blow cooling air over the windings. So obviously, the fan speed is 100% dependent on the motor speed. Step 1, your fancy new VFD lowers the motor's RPM. Step 2, because it's directly attached, that shaft-mounted fan slows down right along with it. Step 3, airflow drops drastically, trapping all that heat inside the casing. And step 4, that trapped heat just builds and builds until the winding insulation literally breaks down, and boom, your motor is destroyed. So the harsh reality here is that running at low speeds for extended periods is a direct threat to that winding insulation. Slowing down a motor does not mean you're giving it a break. Ignoring this physical limitation pretty much guarantees you're going to end up with a melted, dead motor and some incredibly expensive downtime.
So how do engineers actually solve this? Let's look at Section 3. Inverter duty motors explained.
The difference between these motor types isn't some complex wizardry. It's just about the hardware. A standard induction motor uses, well, standard insulation. That makes it super vulnerable to low-speed heat, but hey, it's cheaper to buy. On the flip side, an inverter duty, or VFD-based motor, solves this whole thermal crisis by using vastly superior, much tougher winding insulation. It is explicitly built to survive that low-speed heat when the fan just isn't pushing enough air. But as you might guess, this upgrade comes with a significantly heavier price tag. Because of that cost, we have to look at workarounds. Welcome to Section 4, the minimum speed rule. Since replacing every single standard motor in a factory would cost a fortune, industries use strict operational limits instead. If you're going to run a VFD on a standard induction motor, you must never let it drop below 30% of its rated speed. That is your absolute floor to keep enough cooling air moving. Now, if you did shell out for the upgraded inverter duty motor, you get a bit more breathing room. You can safely push that one down to 20% without risking a meltdown. Let's do some quick mental math to make this super concrete. Picture yourself standing on the factory floor, looking at a standard three-phase induction motor. You check the nameplate. It says the rated speed is 1500 RPM. You've just hooked a VFD up to it. Exactly how slow can you run this thing safely? Well, if we take exactly 30% of that 1500 RPM rated speed, we get our hard line in the sand, 450 RPM. You have to program your VFD so it never ever runs this specific motor below 450 RPM. If you go any slower, that cooling fan is practically useless and the heat is going to start eating away at the windings. Actually, let's look at this from one other angle, because out in the field, you might be programming your VFD using frequency, so hertz, instead of RPM.
Translating that exact same 30% rule into frequency means that if you're starting with a standard 50 Hz motor, you are entering the danger zone if that VFD drops below 15 Hz. 50 Hz is your baseline, 15 Hz is your absolute floor.
Finally, let's bring all this theory back to reality. In Section 5, Practical Industrial Realities. Here is what field engineers actually do out there. Most facilities completely avoid buying those pricey VFD-based motors. The ROI just isn't there for them. Instead, they keep their existing standard motors to save cash, rip out those old, jerky direct online starters, and wire in new VFDs. To keep the motors from catching fire, they just strictly enforce that 30% speed rule. And the secret to why this playbook works so well? 30% still gives you a massive, highly usable range of speed. For almost every normal industrial application out there, you simply don't need to go slower than 30% anyway. So you get the smooth start, you get the speed control, and you save an absolute fortune by keeping your standard motors alive.
So, as we wrap up this explainer, I want you to think about the equipment you're relying on every single day. Take a hard look at your own facility's VFD setups. Are you actually respecting that 30% minimum speed rule for your standard motors? Or are you secretly, quietly risking a catastrophic meltdown right now? Understanding these mechanical limits is quite literally the difference between running a sleek, modernized factory and facing a brutally expensive maintenance disaster. Keep that in mind next time you walk the floor. Thanks for joining me on this deep dive, and keep learning.